So in this video, I'm going to go through an example of a mixing problem where we're able to apply differential equations in order to model what's happening. So we've got a chemical plant which starts pouring water containing 15 grams per litre of salt into a 200 litre tank at a rate of 4 litres per minute. Unfortunately, the tank's already full of rainwater, and an overflow valve lets the contents of the tank into a nearby creek at the same rate of 4 litres per minute. And we're going to be able to assume that the liquid in the tank is evenly mixed. So we're going to go through a process of starting off by drawing ourselves a diagram of what's happening, showing that this here is the differential equation that can describe what's actually happening, and then going through and solving the differential equation eventually. So let's start by doing the first part, which is to draw a diagram showing the tank and all the liquid that's flowing in and out. So I'll pop it down here. So I'll draw myself a little tank. Okay, it tells us that it's even full. So we have some information. It's telling us that this chemical plant is pouring water that's 15 grams per litre of salt into our tank. So therefore the inlet here is going to be, I'll put it as 15 grams per litre of salt, and we've got the size of it, so it's going to be a 200 litre container here. The rate of its pouring is also given in terms of a flow rate, so that's going to be 4 litres per minute. So what we're then told is that we've got this overflow valve that's going to release from the tank, and it's going to release at, we've got 4 litres per minute. All right, so there's like some little tap here, and out of that it's coming at 4 litres per minute, which conveniently is the same amount up here. So the only other thing I think I'm going to mark on this is the amount of salt that we've got. So I'm going to call it X for the amount of salt, but you could pick any letter. And I'm going to measure it in grams. So far we were told that the inlet was a concentration of 15 grams per litre, so that's why I'm picking grams down here. Alright, so our next step is to show that the amount of salt in the tank, which again has been called X here, obeys the differential equation that's given below, where T is measured in minutes. So the overall rate of salt amount changing with respect to time in the tank can be found by using this kind of general equation, where we look at the rate of change of salt into the tank, and then we take away the rate of change of salt out of the tank. So we just need to be aware of the units that all of these are in. All right, X is an amount, which we're measuring in grams, and T is a time, which we're going to measure in minutes. Okay, so all of these are going to be the grams per minute rate of change. So dx dt, all right, is in the equation, so we don't really need to do anything with that. So what I'm going to look at next, though, is if we can get an expression for the rate of salt amount going into the tank with respect to time. So dx on dt in. Now we have a little bit of information, all right, all this stuff here relates to the inlet. So what we're told is that we have a concentration of the flow of 15 grams per litre, and the flow rate is 4 litres per minute. Now what we're looking for is something in the units of grams per minute, and you'll find that if you do these two quantities multiplied together, so concentration times flow rate, you're going to end up with something in the right units that you're looking for. So I'm going to show you. So 15 grams per litre is our concentration, multiplied by 4 litres per minute as our flow rate. You can see that we end up with litres on the top and bottom line, so these are going to cancel out with each other, and we're just left with grams per minute. So overall, 15 times 4 is 60, and the units are what we were looking for. So that's easy for the first one. Now we'll look at the second term, which is getting out the rate of change of salt concentration going out of the tank. So for this, all right, we have this information down here, which relates to our outlet. And again, the units aren't quite what we're looking for. So we want it in grams per minute. We saw it a moment ago that we could take the flow rate and multiply it by the concentration in order to get the right units. So we're given the flow rate, okay, which is the same as this bit. What we need is the concentration of what's coming out of the tank. And this is something that we can compute. So from the information we're given here, we know that we have an X amount of salt in the tank, and the volume of the tank is always going to be that 200, since the inlet and the outlet are matched in their rates of flow in and out. So as a result, the concentration of what's in the tank, call it CONC, it's going to equal the X grams per 200 liters. So X on 200. So this here, all right, if I match it against this, is going to be the grams per liter flowing out of the tank. Okay, and of course, X can change over time, all right, but all it's going to change is the concentration. It's never going to change the flow rate. So if we now apply our equation where we take the concentration and multiply it by the flow rate, so we're going to have our X on 200 grams per liter in the tank, multiplied by the 4 liters per minute. Again, we see the liters cancel on top and bottom line, and we're left with, this is going to be 4x over 200 with the units of, we've got grams per minute, and we can make this a little nicer. So x on 50 is the same as 4x on 200. So that's our outlet. So what we want to do now is go back and substitute what we've found for the rate of salt into the tank and the rate of salt out of the tank into this original equation that we started with. So there we end up with dx on dt is equal to, we replace this with the 60. I'm just going to drop the units and we'll just know that they're all in grams per minute. And here we can replace it with x on 50. And what we should find is that this equation is exactly the same as what we were asked to show back up in the question, as you can see here. So we'll move on to part C here, which is asking us for the initial condition of x of t. So when we talk about initial condition, what we want to know is what's happening at time is equal to 0. So that means we need x, the amount of salt in our tank at this particular time, and we should be able to get that by going back and rereading the question. Now the key sentence for this is that the tank is full of rainwater at the beginning of time. So rainwater, you can assume, has no salt inside it. So therefore, the amount of salt in the tank at the beginning of time, if this is all rainwater, should just be 0 grams. So that would be our initial condition. At time equals 0, x is equal to 0. So we'll jump now onto D. We've got the salty water flowing out into the creek will cause damage when the salt concentration reaches 5 grams per liter. So from this, we need to figure out what the value of x will be when this occurs. So 5 grams per liter, this here is the concentration of our essentially our solution inside the tank. So what we need to do is figure out what value of x divided by 200 would give us the 5 grams per liter, okay? Because we said that concentration was equal to x on 200. So if we substitute this in for our concentration, pop it over here, so this is part D. We're going to set our concentration to be equal to 5, and we just now need to rearrange for x. So if we multiply the 200 up to the other side, we're going to get 5 times 200, which is the same as 1,000. So that's telling us that when the amount of salt in this tank hits 1,000 grams, that's when we're exceeding the salt concentration of what's allowed to flow out. So the last bit here is to solve the differential equation to find the time when the salty water flowing into the creek causes damage. Alright, so this is where we get a little bit involved. What I'm going to start off with is solving this for the general solution. Once we've got that, we'll apply our conditions in order to find the unique solution. And then we'll do the last bit, which is solving for the time when the concentration hits 1,000. So starting off with this here as our equation, if we want to solve it, we're going to use our separation method where we need to separate the x's and the t's across the equal sign. So how I might start that off is multiplying everything by dt. So that's going to leave dx on the left, and all of this gets multiplied by the dt. Now I need to make sure all the x's are on the same side of the equation. So to make that happen, I'm going to divide by what's in the brackets here, so the 60 minus x on 50. So when that comes to the other side, it's going to end up being 1 over the 60 minus x on 50 dx. The only thing left on the right then is dt. So at this point, I can see that I've achieved my separation goal. So what I can do is integrate both sides. So integrating, and remember, if it helps you, you can consider this as the integral of 1 with respect to time, because 1 times anything is just the anything. You haven't done anything to modify the equation. Alright, so when we integrate this one, it's going to be a little bit messy. We can see that the x is on the bottom line, so that's going to tell us that we're going to end up with a log falling out. And as an initial guess, I just make it whatever's in the brackets. Whatever's in the bottom line in the brackets. Okay, so we end up with log of 60 minus x on 50. However, if we know that if we take the derivative of this, it should go back to what we started with, and it's not going to in the current form. If we take the derivative of this, it will go to 1 over 60 minus x on 50, but then we need to multiply according to the chain rule of the derivative of this inner function. So the derivative of the inner function would be negative 1 on 50 from here. So in order to compensate for that, what we need to do is put essentially a constant out the front here, and that constant is going to be negative 50. So I'll come across and pop it in here. So let's just do a quick check off to the side here. So if we took the derivative of this, the negative 50 would stay out the front. The derivative of natural log goes to 1 on whatever's inside it. But then we need to multiply by the derivative of this inner function, and that would be the negative 1 on 50 that sits out the front of the x. So now what we can see is we've got 50 and 50, top and bottom line, so they cancel each other out. And the negatives here also cancel each other out. So it just goes to essentially what we started with, okay, which is correct. You could equally do the more longer-handed way of integration by substitution in order to show that this was the case as well. But I'm going to leave it like that for this example. And now we've got an easy one to integrate. The integral of 1 with respect to t is going to be just t. And because we've done indefinite integration, we need to make sure we pick up the little constant. So we have the plus c. So now the challenging bit is kind of over, and the rest of it is just rearranging to get x on its own for the general solution to our differential equation. So how I'm going to start by doing that is dividing by negative 50. So if we do that, it moves to the other side, and we're going to end up with negative 1 on 50. I'll put it as t plus c in brackets. So next we see that our x is inside the log. So in order to get it out, we need to play around with those power rules. And if we do e to the power of natural log, what we know is that the natural log and the e kind of cancel each other out. And all that we get left with is what's up in here. We just need to make sure we do it to both sides of the equation to keep it equal. Oops. So that means that we do, e to the power of all of this. So we said the e and the log cancel, so we're just left with the 60 minus x on 50 is equal to the other side. The next thing I might do is I'll make the 60 swing to the other side of the equation, so it's going to end up with negative x on 50 is equal to all of this minus the 60. What I'm going to do next is I'm going to multiply everything by negative 50. So that should eliminate the negative and the 50 on the bottom line at the same time. So this becomes x. This gets multiplied by negative 50, so I'll pop it out the front. And then negative 60 times negative 50 is going to become positive 3,000. So this here would be a valid general solution to my differential equation. But what I'm going to do is take it one step further and think about how I can kind of bring this constant c outside of being in a power. Okay, so this is just to make it a little bit nicer, so in a moment when we substitute in our condition, we get a nicer number for it. So what we can do is we can essentially expand out this bracket, which would mean it would become e to the, I'll put this as negative t on 50, plus we're going to get what's going to be negative c on 50. And we still have that 3,000 on the end. So next I'm going to separate these, remembering that there's the rule where if you have a to the b times a to the c, you can equally write it as a to the b plus c. So here we've got the plus kind of version, and we're going to separate it out to what's on the left-hand side. So that means we're going to get e to the first term, which is negative t on 50, multiplied by e to the second term. Now the key here is that e is just a number, it's 2.71 blah blah blah, lots of decimal places. C is just a number, it's a constant at this stage, and 50 is just a number. So rather than writing it in this way, what we can do is introduce a new variable. I'm going to call mine a, which is just going to combine all of this together, so e to the negative c on 50. So that means we can write it a little bit nicer. So actually I'm going to stick this in here, so 50a plus 3000. So that's our nice form of the general solution to the differential equation. Alright, general because we don't actually know what a is at the moment. So I'll mark in here, this is the general one. So how we go from general to unique is that we look at our condition. And we had a condition that we found out way back up here, this one here. So we know that at time is equal to 0, the amount in our tank of salt is equal to 0. So if we come down and use that, we should be able to figure out what a is. So let's go ahead and substitute this in. So x is going to 0, and time is going to 0. So here we've got e to the power of 0, and we know that anything to the power of 0 is 1. So this is just going to simplify to 50a, and then we've got our plus 3000. So we just need to rearrange for a. If I swing that term to the other side, it goes positive. I'm going to get a is equal to 3000 divided by 50, which is 60 over all. So we've now got what our constant is. So if we substitute it back up in here, we're going to get x is equal to negative 50 multiplied by a, which is 60, e to the negative t on 50. And I can write that a little bit nicer by just popping these numbers together. So overall that's negative 3000. So what I've solved for here now is my unique solution to the differential equation, because it fits for both, I'll go back. This is the solution to the differential equation that fits both the differential equation itself as well as meeting the condition that at t equals 0, x is equal to 0. So the final step here was to figure out when it actually became dangerous to release. Okay, so it wanted us to find out when the salty water flowing into the creek causes damage. Now, based on the work we did back in part D, we found that damage occurred when X hit 1,000 grams. So that's what we need to substitute in and just figure out what time is when X equals 1,000. So when T equals whatever, X equals 1,000 grams. So let's go ahead and do that. So 1,000 is equal to all of this stuff. So what I might do is take this to the other side, which makes it positive, e to the negative t on 50. And then at the same time, I might bring this to the other side, and that's a constant that can combine with the 3,000. So 3,000 minus 1,000 is 2,000. What I might do next is divide by 3,000. So I'm going to get 2,000 divided by 3,000, which is the same as 2/3. I'm trying to get t on its own here, so since it's tied up in the power, I know that if I perform the log, since it's already raised to the power of e, it should cancel out the e in the log. And we need to do the same thing on both sides of the equation to keep it equal, so we take the log here as well. So log and e cancel, and we just end up with whatever's up the top here. So negative t on 50 is equal to the log of 2 on 3. What I might do next is if I multiply everything by negative 50, it should get rid of the negative in the 50 here. So t equals, negative 50 multiplied by log 2 on 3. And if I type this into a calculator, I'll end up with my time. And this is approximately 20.27, and the units are in minutes, since that was what we were working with from the beginning. So that there is the answer to the question. Now, if you wanted to verify it visually using a graph, what you could do is go back and plot your unique solution. And I've done it here in Wolfram Alpha. So this here is just the equation. And if you have a look at it, this is how the amount x is going to vary over time t. Now, that's a bit of a zoomed out view. So over here, I've told it to look at it just from t is 0 to t is 30. So we get a bit better view here. What we were interested in is when x goes to 1000, all right, what the time is equal to. And we can see here that from the plot it looks like it's about 20 minutes, which is what we got from doing the calculations as well. So it's a good double check that we've got the right thing. So that's all there is.